All right, now here's another related phenomenon. Okay, what this diagram shows you is a magnetic field into the sheet of the paper. Here's a metal bar. Okay, now if you move this metal bar in this to the right, and it'll take a force to move the metal bar, what will end up happening is the free charges, the, um, the, the positive charges will end up there, and the electrons will, and the negative charges will end up there. So again, you have a magnetic field that's going into the plane of the paper, and you take a metal bar and move it to the right. You'll need a force to do that. And as long as you're moving it to the right, this is acting like a battery, with this end being positive and this end being negative. Okay, so positive charges will collect there and negative charges will collect there. So if this were a piece of metal, all that's happening is all the electrons, some of the free electrons will collect here, and this end will become positive. Okay? And the voltage, induced voltage, so this will act like a battery, this rod will act like a battery, and the voltage will be B times L times V. L is the length of the rod, and V is the velocity of the rod. And again, this expression is good as long as this velocity is perpendicular to the magnetic field. It turns out that if the velocity were parallel to the magnetic field, so if you took this rod and moved it parallel to the magnetic field, the voltage, there would not be any voltage induced. Okay? So this expression is good only when you're moving. And if you move it at an angle, then what would be true is there would be a sine theta term there. Okay. But anyways, so we are going to move this wire perpendicular to the magnetic field, and so it's BLV. Okay, so this rod is acting like a battery. Okay, so again, so now we place the rod on rails, and what we're showing is if you move the rod in that direction, it will induce a current in this direction. Remember, that was the positive end of the battery, this was the negative end, and current flows like this. And there's a current. Okay, so now here's a way to think about it. When you move this rod, see the flux through this area is changing because the area of this loop is changing, and that is inducing that current. Okay, so we could use Faraday's law to explain this. Okay, so the EMF induced is rate of change of flux. The flux through this loop is B times the area. The area of that loop is Lx. Okay, x is that distance, and if you take the time derivative of that, dx by dt is velocity v. Okay. So there's the induced EMF. So this rod is acting like that battery, and the EMF of the battery is BLV. So now what we are going to show in the next two slides is, so the question arises, let's say we put this rod on a frictionless rail, just give this a velocity, and if the rails were frictionless, once you gave it velocity, it should keep moving, and then you get free energy out of it. But it turns out that, so that's what we're going to show you, that you need to apply a force to keep it moving, and so the work done by you on the rod is converted to electrical energy. Okay. So when a current moves through this rod, because this current is going in the moving, this current is in the presence of a magnetic field, the magnetic force is in that direction. And that's why you have to apply a force to keep the rod moving, to balance this magnetic force. Okay. So you're doing work against this magnetic force. Okay. So because the induced current magnetic force arises on the moving conductor, a force must be applied to keep the conductor moving at constant speed. Okay. So let me show you this simulation. Okay, so here's the applied force, and when soon as you start moving the applied force. So, and you see the input power is equal to the electrical power to the resistor. So whatever you're putting in is what you're getting out. So what you're doing is, so this is what do you call those things? So this is sort of a transformer in the sense that it's transforming one form of energy to electrical energy. Okay? So it's an energy transformer. Now the word transformer is used in a different sense in electrical engineering, but I'm using it in the sense, a transformer in the sense that it's converting one form of energy to another form of energy. So your input power got converted to electrical power. Okay. All right. So again, what we said was, why did you have to apply the force as soon as the current started flowing? You had this magnetic force to the left, and you had to do work against that magnetic force. So you had to apply this force against the magnetic force. Okay. So here was the input power, applied force times the velocity. The applied force was equal to the magnetic force, and the magnetic force is given by ILBV, and BLV was the EMF. So this was the electrical output. So this was the electrical energy. So the power you put in is equal to the electrical energy you got out. Okay. Again, no free lunch ever. Whatever you put in is what you get out. Okay. So the Lenz's law tells you the direction of the current. So as this thing moves to the right, the flux through this thing is increasing. So if you have a current in this direction, which will produce a flux out of the sheet of the paper. Okay, so the current will be in this direction, and if you move the conductor in this direction, the current will be in that direction. All right, so this fact that we stated, if you move a conductor in a magnetic field, a voltage is induced between the ends, and the voltage is equal to B, the magnetic field strength, times the length of the conductor times the velocity. Okay. So NASA did an experiment like this back in 1996. Okay. And so here's the space shuttle in orbit. And the space shuttle goes roughly, used to go roughly 18,000 miles an hour. And here was a satellite tethered to the space shuttle via a 20-kilometer cable. Okay. So here is the space shuttle going at 20 kilometers, 20,000 miles per hour. So the velocity of the space shuttle was about 7.6 kilometers per second. The cable length was 20 kilometers. Okay, 20 kilometers. So L is 20,000 meters. And the Earth's magnetic field is about 0.5 Gauss, which is 5 times 10 to the minus 5 Tesla. Okay, so the voltage between these between the ends of the cable should have been 7.8 kilovolts, and voltage of 3.5 kilovolts was measured by the astronauts. Okay, like a lot of charge leaks away from here because of the conducting nature of the atmosphere at that location. All right, I am going to pause recording for a second.